Well, hello and welcome YouTube. You're watching Mr. Robbins' Q&A Power Hour. This is for Integrated Math 2 material. Now, the Q&A Power Hour is a way where my students ask questions for me and I answer questions back for them. We cover 2 weeks worth of material where they can ask those kinds of questions. I like them to ask content-based questions, and I hope that they learn a little something in return, maybe something that wasn't able to be covered in class, or it's really peculiar just to them, or something that piques their interest that we want to explore something a little bit further, which I'm always looking to do. Now, I'll kind of let them know whether or not they receive credit for the question that they asked because of its relevance, its appropriateness, and its just relating to content. Sometimes I get questions that are more curriculum related, or something else that they're interested in knowing about me or something like that, which I love to still answer, and I will still answer those time to time, but I want to make sure that I'm still answering the math portions first. So without further ado, I hope this one goes less than an hour here. Let's check it out. Now, I haven't seen these questions. They are asked and answered the order that they're received. They submit it in a form for me. So we'll see how these things go. Our units we've been covering had to do a lot with quadratics so far. The unit before, I think just a unit before, we did things on polynomials, adding, subtracting, binomials and such. And I might even have a video on that stuff in the last couple of weeks if you want to take a look at that. We've been dealing with quadratics lately, mostly graphing them out of vertex form, and they recently learned standard form using the vertex negative b over 2a stuff. If you know what I'm talking about there, that might be helpful. So let's take a look at this first question here. And the first question is, how do you find the minimum and maximum value? So if they're referring to a parabola, let me just start with this concept here, and I'll give you a couple quick examples after. Here's a right side up parabola, a U shape that's going upward, smiley face. There's a vertex down at the bottom, right? That is the lowest point that this parabola ever hits. That means this is reaching a minimum value. The y value of the vertex is the minimum value. If you're in vertex form, it's the k value. Here's an upside down parabola, frowny face. And it has a high point, that's the vertex. That high vertex point right there is the maximum of this guy. It's the y value that it hits, which is the k value. A right side up parabola does not have a maximum. It goes up forever. There is no maximum. The maximum's not infinity. There is no maximum. Maximum's a value. Infinity's not a value. The upside down parabola has no minimum as it goes down forever for the same exact reason. So the maximum or minimum occurs at the vertex, and it is a minimum if it's an upside down, if it's a right side up parabola, and it's a maximum if it's an upside down parabola, like that. So just for an example here, really briefly, if I have some sort of graph like this, parabola like that guy, and this is crossing at 5, -6, there is a minimum here at -6. It's the y value. Okay, I think that's really the only example I want to cover here. An upside down one would have a maximum at the vertex value. So that's how you find it. That's how you determine it there. Okay, hope that answered that one. With that one down, let's move on to the next question. And the next question that's asked is, when changing the equation from vertex form to standard form, or finding vertex form itself, what shortcuts are there to lower work time? Well, if you're talking about writing vertex form out of a table, like a table of values, if you're given the, oh gosh, what is it? Like you're trying to find the a. Okay, time out. Let me think about how I want to answer this one right here, because there are 2 questions. One, okay, let me answer in order that you asked it. Vertex form to standard form. So the general form, and I know I'm going to bring them up again, so I might as well write them now. So the general vertex form of a quadratic equation looks like this. The vertex is at hk. Your vertical stretch factor is a. Standard form looks like ax squared plus bx plus c. Again, this is of a quadratic equation. C is your y-intercept. A is your stretch factor. Negative b over 2a can be used to find the vertex, right? And you're asking, and I'll give you a specific example, but you're asking to go from this equation to do some work to get to this equation. What's the fastest way to do it? The steps that occur are the following. You have to square this guy, and then after you get the trinomial out from squaring, you distribute the a into the 3 terms there, and then you combine like terms with whatever the constant is with that k value of your vertex. So there are 3 steps to go there. Now you have to do those 3 steps. There is no way around that. Some people ask how to do those 3 steps faster, though, to still do the 3 steps faster. Some students watch me do it like it's nothing. Like, here, I'll make up a problem right now, and I promise there's no foresight for me with this answer. Let me get this out of the way. Let's do y equals negative 3 times x plus 8 quantity squared minus 7. I just made that up off the top of my head. All right, the standard form here is going to be y equals negative 3x squared minus 48x. Oh, shoot, timeout. Hang on a second. This is a bigger number. Minus 199, if I did that right. So I'll show you the steps in between that you would do, and I'll show you how I just did that. Now, some of that was mental math. I didn't know I was going to be dealing with large numbers. See, I made this one up. First, I square x plus 8 quantity squared. Now, a lot of people, when you square it, is they're going to be foiling this thing, x plus 8 times x plus 8. So x times x is x squared. X times 8 is 8x. Well, let me do this over here. X squared, 8x. And 8 times x is 8x, and 8 times 8 is 64. So that becomes x squared plus 16x when you combine like terms, plus 64. That's inside of this quantity that's being multiplied by negative 3. Then you distribute the negative 3 here, and you get negative 3x squared minus 48x, and this is the part I was having trouble with, minus 192. Minus 7. Negative 192 minus 7 is negative 199. So those are the kind of 3 steps. 1, 2, 3. So, mosquito. So the question is, hold on. I don't know where it went. I'll keep my hat by me. It was bugging me earlier too. So the question is, how did I do that faster? How could you do that? How could you do that faster? Part of it is, well, you have to trust that you're doing your own math right. Like I was trusting I got negative 199 correctly. Things like that. So you have to trust some of your math if you are actually going to skip steps. But the one step that is skipped entirely that really helped me was the first one. X plus 8 quantity squared. And not foiling, but rather using a property that I have used in the past. So let me erase some of the stuff again. And x plus 8 quantity squared, it follows the a plus b quantity squared mentality. Any a plus b quantity squared becomes the perfect square trinomial that is a squared plus 2ab plus b squared. That means you square the first term, you square the last term, and then you double the product of these two. X times 8 is 8x. So when I write this next step here, which is what one I would do mentally, but when I write this next step, I square the x, I square the 8, and I double 8 times x, so it's 16x. So I'm doing that in my head, and I've done this so much, it's like clockwork. If you've seen enough of these things that you square, then you'll know which ones are what because you've seen them a lot. Half the time I'm not even calculating something. I just know that this is that. Now the next thing I'm doing in my head is I am multiplying. I'm kind of doing the negative 3 first, and this sounds kind of weird. This sounds kind of weird because I can't distribute negative 3 into here first. I acknowledge that. But what I'm really doing is I'm really distributing negative 3 into a blank canvas. I'm saying, okay, I want to figure out what because the first thing I wrote was really fast, right? I said y equals negative 3x squared. First thing I did was I said the negative 3 is going into the first term of this squared thing. So I say, okay, the first term of this squared trinomial is going to be x squared. That's when I got down to that. Then I say I'm going to distribute the negative 3 into, and then my mind's coming up with what the next term is. This is x squared plus 16x plus 64. So the next one is 16x. 3 times 16 is 48 because it's negative. It becomes negative 48x. And then the third one was where I had to do 64 times 3. I said negative 3 times 64 here. And I was doing 180. 3 times 60 is 180. 3 times 4 is 12. 180 plus 12 is 192. So that's 192, but remember there's a negative 192, but there's a minus 7 that gets involved as well. So negative 192 minus 7 is the same as 192 plus 7 with the opposite answer. So I'm doing things, the primary bit is this. This is what's going to speed it up. And if you're keen on skipping steps, that's your call. If you have to write out the steps, it's not going to take much less time than what I did. because you still have to write them, and you still have to know how to calculate. So when I did 3 times 64 and stuff, you still have to know how to calculate that stuff. So doing it faster really is just what that first step involved there, or doing what I said after. I'm distributing into the things that I'll create because I trust that I know how to create that trinomial out in my head. So it's through practice and trust in your math and the things you can do. All right, thank you for the question. Here's the next one. On a test, if I get coordinates that are more than the numbers on a graph, what do I do? I guess you mean if you are plotting, if you calculate and compute a point that goes beyond your graphing window, I would find extra points that fit in your graphing window. If they don't fit in your graphing window, then you've graphed as many as you could. Now, on a test, when I ask you to get up to 5 points, or a minimum of 5 points, to get 5 points on there, if you can only fit 3 on them, my guess is you might have done something wrong on your graph, if you know what I mean. If my goal is to get you to plot 5 points on there and you can't fit them, then I didn't achieve my goal in asking you to get that, which is less likely because I would have gone over that test to make sure that the test asked the question in the right way. So if you can only fit 3 points on there, consider that you might not have flipped it over. Your stretch factor might have gone too large for a weird reason with order of operations or opposite same and putting something in the wrong direction. So just keep that in mind. But yeah, what do? I mean, you can have it in your table. That's great. But if you can't fit it, don't. Now there are times, and I have a little graph thing with me. I just have it off to the side. I'm going to drag it in and get rid of this one. There are times where there's a point that's maybe 1 or 2 things that's just above your graph. So let's say it's like let's see, let me shrink this a little bit. So let's say I have a parabola that's maybe like right here, and then I have my 1, 1, 2, 4, 3, 9. Let's see, here's 4, 5, 6, 7, 8. Uh-oh, it doesn't fit. Well, 1 more up doesn't hurt, right? You can fit that. If it's 4 more off, then it's kind of hard to count that and really fit on it, or it leaks into another problem. But I could fit 1 more point off there if I absolutely had to. I understand the spacing here. I'm decent enough there, and it helps me with my accuracy of my graph even more if it's there than if it's not. So if it's just 1 or 2 off there, I'm sure you could fit it. Otherwise, just try and get more points on the other side if you're able to. And remember, if you are using a table, to not just automatically have 0 as your middle point in your table, build it around your vertex. See, if I had 0 as my middle point, I did -2, -1, or -1, -2, and +1, +2. +1, +2 would go way off this graph here because they'd be way high up. You want to build around -3. Plug in -2, -1, and 0. Plug in -4, -5, -6. That's fine. So build around the table to start with if you're using a table, and then kind of go in that way. All right, the next question here says, on the homework for 6.3, this might be a specific question. On the homework for 6.3, I was having a hard time figuring out number 21. I don't know these. Number 21 on page 249. I kept getting a fraction, so I tried using a different x and y, and each time I still got a different answer. So my question to you is, can we use different x and y pairs and still get the right answer, or do we have to use a specific x and y pair? I have my book once. I have my book down here. Give me 1 sec. I don't like doing this. I don't like looking up a specific problem here because I just don't. To your credit, asking this question won't be fully maximized unless you ask more questions on here. What page? 249. Oh, you're writing. Oh, you know what? And I didn't answer the other person's question about the what shortcuts are there to go finding vertex form itself. Let me answer this question first because I didn't yet. What shortcuts are there to lower out and finding vertex form? There is a tableless method of finding vertex the same way we do tableless graphing. I just can't teach it right now because we're distance learning, and I can't account for how you're getting your information, so I need to see work. So I'll show you another way after this unit, and then you can check it out. Or if we go back to class physically, I'll show you then. You know what I mean? I just can't show you now. But it has to do with understanding your 1, 1, 2, 4, 3, 9 stretch factor parent function stuff. That's all I'm going to say on that. Now with this, we are trying to find the a value, write it in vertex form, do standard form, stuff like that. So you said you were getting a fraction. I assume you mean for a. and a is not a fraction on this one. So I don't know what you substitute and where you put things into. You have to make sure that you adhere to signs, make sure your signs are correct, and make sure things are placed in the correct spot. So let me look to this problem and convince you that the answer shouldn't get different, because your question to me was, do you have to choose a specific xy pair? Sorry, I thought I saw a mosquito in the corner of my eye. The answer is definitely no. No, you do not have to choose a specific xy pair. If you choose any xy pair, you should get the same answer. So here we have -1 through -5 for x, I think. And y we have -6, 6, 10, 6, -6. And they tell you that the vertex is at, I think, -3, 10. Yes. Okay, I'm going to put this thing down. Ugh, don't want that. All right. So what we do is we use this vertex form, y equals a times h, x minus h quantity squared plus k. We have to find out what stretch factor applies for a graph whose vertex hk value is at -310. And you have these different xy pairs that you can plug in. Now, I don't know if you were doing this portion right specifically, but if you choose -4 for x, you have to choose 6 for y. I can't just choose -4 for x and -6 for y, or 10 for y, something like that. I have to choose that. Also, I have to choose something that's not the vertex. So -310 is going to go in for h and k, and I can choose -4, 6 for x, which I'll start with. Let's start with -4, 6 for x. For x and y, excuse me. Here's x, here's y. So y is 6. Maybe this way you had backwards. Maybe 6 goes in for y, but since y is written on the left here and on the right here, you might have written -4. Who knows? That can happen as well. But 6 equals, we're going to solve for a, figure out what the stretch factor is here. I got x, which is -4, minus h, which is minus -3, that's plus 3, squared, and then plus 10. For time's sake, I'm not going to show all the steps here. If I subtract 10 from both sides, I get -4. -4 plus 3 is -1. Quantity squared is +1. So you get a equals -4. Okay, so your final equation then is y equals -4 times x plus 3, quantity squared minus 10. Now that was just one of the versions right there. Let's try another one instead. Instead of plugging in -4, 6 for x and y, let's try and substitute -5, -6 for x and y. Maybe after this one, you'll feel convinced enough that 2 of them worked out and the other 2 should. Because of the symmetry. You can tell here, 6, 6, -6, -6. And these are each constant change. 1 away, 1 away, 1 away, 1 away. So -5, -6. I'll get -6 for y, -5 for x here. -6 minus 10 is -16 here. -5 plus 3 is -2. -2 quantity squared is +4. So -16 is 4a. Divide both sides by 4. I get a equals -4 again. So I'm still getting that same answer there. So anyway, something happened for you on it. I'm not sure specifically what. Could have been a substitution, something wrong. Could have been you try to add a 10 to whatever number you get here that couldn't combine. There are a lot of different things that could occur, but no matter what you plug in, you should still get the same answer with that, no matter what happens. So I hope I answered your question there. Okay, you will get credit for the thing that you put. What I didn't like is you made me hunt for a problem, although it sounded like your question was more generic. It's not like you had a focus in your question, so that's good. I appreciate that. You will get credit for that, just I don't like hunting. All right, the next question says, do I have to reverse x in the vertex in a parabola? If you're talking about writing vertex form, the whole vertex is opposite the same thing. Well, yeah, if you're in vertex form, like this one I have right here, if we're in vertex form, the opposite of -h is +h. There's a reason why it's opposite same that I answered in the last video, and it's kind of probably different than you think. It's not just made up why it's opposite same. There's a whole reason behind it that I really do answer, so you might want to take a look at that. So yeah, the vertex here is at hk, so you reverse the x opposite of what's in the form. If that's what you're asking, there you go. What else could you be asking there? What do I have to reverse x in the vertex in a parabola? In the vertex. I think that's what you're asking about. Do you have to do that? I mean, yeah, otherwise it's a different graph, right? That's not the graph for it. If this is x minus 2, quantity squared, whatever, plus 3, then your vertex is at 2, 3. It's the opposite of what that is. Can't think of what else you might be asking for. Do I have to reverse it? There's a reason for it. I covered it in the last video if you do want to check it out. There is a reason for it. But yeah, you do. And if you were asking something else, I'm not sure what it was. I'm sorry. All right, let me kind of scroll down a little bit. So here we go. How can you tell what is the correct description of a graph when asked to describe it? So we're talking about quadratics one more time here. And if you're in vertex form specifically, there are really three kinds of things that we look for with a description. It's number one, based on reflection. Number two, based on a stretch or compression. And these kind of come hand in hand because they both have to do with the A value. Sorry about my handwriting right now. Number three is translation. And that has to do with both H and K. So let me put that. I'll say reflection has to do with the, I'll just say A. Stretch compression has to do with A. And translation has to do with H and K. So now it says, how can you tell what is the correct description? Because we did quizzes and tests where there's multiple choice and you have to match what's what. Reflection is all based on whether you're a positive or negative sign on A. If it's positive, it's a right side up parabola. If it's negative, it's an upside down parabola. That's it. So you reflect across the x-axis when you go from something that's positive to something that's negative. See, here's the x-axis right here, and you reflect over. That's what flips it over that way. Okay? That's the reflection piece. The other part of A is stretch or compression. If A, I'm going to specifically say the absolute value of A, because it doesn't matter if A is positive or negative. If the absolute value of A is greater than 1, it's a stretch. That means, and vertical stretch, by the way. Everything we're talking about is vertically stretching or compressing. I think this bug did bite me. I think it got me near my elbow here. If A is between 0 and 1, remember, just negating sign, but if A is between 0 and 1, it's a compression because it has shrunk vertically. It's gotten smaller. And finally, HK is the vertex bit. So you know where to plot a vertex, and we're talking about with relation to the original parent function f of x equals x squared, which starts at the origin. If a vertex starts at the origin, and you have a point like 2, 3 on that last one, that means you go right 2 and up 3. And the translation description really talks about that. So if you know how to graph a vertex in general, then you know which directions you went from the vertex to do it. Over 2, up 3. That's right and up. You know what I mean? Or left and up, left and down, whatever it is. So translation part, I think you get the most. But just based on those three descriptions there, is your A value positive or negative? Is it more than 1 or less than 1? And how do you do your vertex? And that's how they'll be talked about. And those words matter, right? Stretch, making it taller, compress, making it smaller. It's all about the vertical stuff there. And x-axis is what we reflect across. X-axis is what we reflect. Remember, it's your mirror. We go up and down, but the mirror is a left to right to go over. Okay. How does the 1, 1, 2, 4, 3, 9 method relate to the table for lessons 6, 1 and 6, 2? To be more clear, I know it's easier, but how are we using it without knowing its origins or relations to the table method? I tied in. No. I definitely gave you origins to the table method here. In fact, that's how we started. Very first thing in section 6.1, I absolutely started by saying, let's graph f of x equals x squared. And then we did f of x equals 2x squared. And actually, everything from 6.1 was vertex at the origin. So all we played with were stretch factors to begin with. And then we said, hey, there's a pattern here. So everything was based on the understanding on the table from f of x equals x squared that when you square certain numbers, here's what comes out. You square 0, you get 0. That's always going to be the case. 1 squared is 1, 2 squared is 4, 3 squared is 9, things like that. That's how we get these values here. The thing is, when you apply a 2, the multiplication comes after the exponentiation. So we double after the fact. We absolutely did this here. And we talked about, hey, all these heights that were here, instead of going up 1, now you go up 2. Instead of going up 4, now you go up 8. Instead of going up 9, now you go up 18. And everything is doubled what it was before, even as you go over the same amounts here. So that's no different than what we talked about before. Instead of 1, 1, it's 1, 2. Instead of 2, 4, it's 2, 8. Instead of 3, 9, it's 3, 18. Now listen, I'm happy to talk to you about it again. I just want to make sure that you're understanding. No, we did this. We did. And furthermore, we started to do it in section, I guess you're talking about 6.2. I hope that's the vertex form one. We started talking about in vertex form here in a lot of different ways. First of all, we tied it in with your, one second. we tied it in with your absolute value graphs. Everyone was free and willing to graph absolute value graphs and just understand you use slope without asking questions about it and not plugging it into a table. Do you guys know why you're allowed to go up 2 and over 3 when your slope is 2/3? I mean, I'm genuinely curious. Do you actually know why you're allowed to go up 2 and over 3? I mean, I hope you do. I'm just saying that if you don't, that's something you went on without processing as well, and when it's easier to do, right? Now, with this one here, it's the same concept. You still have a vertex at HK, and we apply it the same way we would do here, but everything is in relation to the vertex. Because now if we start at the vertex, that means we're already k units up or down. Now, when we go 1 away from our vertex, h, that's when we're plugging in specific numbers. So let's say I did this example earlier. Let's say I had, let's keep a as 1. X minus 2 quantity squared plus 3. So if you use a table, remember you want to have your vertex point in the middle. This is if you use a table. Now your vertex is at 2, 3. So vertex at 2, 3 right here. So I want my vertex in the middle where I'll do 3 and 4 and 1 and 0 like that. Oh, I guess we're back where we were, right? The vertex is right in the middle. So vertex 2 and 3, plug 2 into the stuff and you get 3 out clearly because that was the vertex. And when you substitute 3 into here, keep in mind, here's a 1. When you substitute 3 in for x, it's the same thing as me when I'm graphing saying you go 1 over. Okay, so I want you to look at it this way right here. I'm going to shrink this graph and bring it in. I think the bug landed on me. I really think I got bit here in my elbow. It's pretty itchy now. It's psychological. So my vertex is at 2, 3, and I talk about this kind of thing here, 2, 3. I say 1 over 1 up. From the vertex, 2 over 4 up, 3 over 9 up, things like that. You might say, let's plug in 3. Now, when you substitute 3 into here for x, we get 1 times the quantity 3 minus 2 squared plus 3. Now, 3 minus 2 is 1. Notice we didn't square the number 3. We squared the number 1. Just like I would square the number 1 when I say I go up 1 squared. We multiply that by 1 as the stretch factor here, meaning it's just going up 1. We're not going to change anything else. We're not going to double our height or anything like that. But notice if this was a 2, that would mean that amount would get doubled. Now the plus 3 comes after the fact, meaning we'd go 3 up from the origin place or from wherever we're at. But if I'm already 3 up from where I start, then it's kind of like I did the plus 3 to begin with. But it's not being doubled. It's not being affected because I'm talking about how much I'm going up from the vertex, not from the x-axis. I'm not saying I go up, twice as much as I would like 4 right here. I'm going up twice as much as right here. So the x value that I plug in is not the number that I square. It's the distance from the vertex. 3 minus 2 is 1. 1 is the distance from the vertex. I go up the amount that I get squared from what I subtracted from the distance, and I double or multiply by 1 from whatever it is with stretch factor, just like you would have to here. And the plus 3 I already took care of at my vertex. So yes, I definitely talked about these things already before. I'm glad to go over it again, but just they're definitely covered even in class when we did it. Maybe it's on the last Q&A Power Hour video they talk about this stuff as well, but it was covered, and it was covered in small bits at a time. First, we started with original parent function, vertex at the origin. Then we started talking about transformations and specifically why this is part of why it's opposite inside here, because this is distance from vertex. This means distance from vertex on the x value that you choose. And then the plus 3 kind of is applied first. But anyway, so all that's there. It does make it easier. You said it's easier. But you are knowing its origins. And my question to you is, do you know the origins of slope? Do you know why for its slope of 2/3 you go up 2 over 3? I am curious. And I don't know who asked this. I'm just curious, the person who asked this, if you know. Because if you don't, I'm wondering if you have questions on that now. Okay. Anyway, let's keep moving. All right, I've always been so confused with negative numbers and how to add them. Like, how do you know if it'll be positive or negative? I appreciate the question. I don't know if it's really related to our content. I mean, it always is, but I don't know if it's really content specific. I'd always say, hey, use a calculator at this point. But let's, I could get super deep into this, and I'm going to try not to. Let's go in this form right now. Let's assume that letters A and B are positive numbers. Okay? Assume A and B are positive numbers. For my sake when I do these things. Okay? That would mean that A plus B is a positive result. if they're both positive, right? Negative a minus b will always be a negative result. Okay, negative a minus b is the same thing as the opposite of a plus b. So if you have trouble with negatives, if they're both negative, that's going left and then left some more. Just like with positives, it's going right and then right some more. So you can think of it as addition when you calculate it. Just remember to make a negative answer. So when I ask you, hey, what's negative 19 minus 8? Do negative 19 plus 8. You don't have to write this, but in your head, do 19 plus 8, which is 27, and then make your answer negative. So it's negative 27. It's always a negative answer because it's going further negative. The big questions become, what happens when you do a minus b, or negative a plus b, b minus a, things like that. This is all dependent on the size of your numbers. Obviously, well, and look, a minus b is a clear and easy one. If a is a bigger number, like 5 minus 3, well, the answer is positive. It's 2. So you might have trouble computing its value, though, right? What if a is smaller? What if you have 3 minus 5? I mean, clearly the answer is negative because you lost more than you gained, right? I gained 3 pounds and then I lost 5 pounds. What's my net overall weight change? And I guess it's a good thing to lose pounds for some people, or gain, just depending on who you are. But anyway, so here overall, I lost 2 pounds. 3 minus 5, just like this last one right here, it's the opposite of 5 minus 3. 5 minus 3 is 2, so this one's negative 2, right? That's where we get that. So this is a nice way to kind of compute some of these things. If the signs are opposite, and here's just what I recommend. If the signs are opposite, then it's always going to be a subtraction in your eyes, meaning your number's going to get closer to 0 in some capacity. In some capacity, it'll be closer to 0 than the result of your largest number that you have. Like it'll have crossed 0 or it'll have gotten closer. So 0 will somehow be involved. Your sign will either become the opposite sign or whatever else. So always treat it like subtraction. I mean, clearly 3 minus 5 is subtraction, but treat it like subtraction that you well know. I know 5 minus 3. I'll do big minus small. Just know that my answer is negative. So that kind of stuff can kind of help you there a little bit. And again, I don't want to dwell on this thing too much, but that's kind of an idea. When you have something like this, what if I had negative 3 plus 5 and you get kind of confused like that? Well, remember that addition is commutative, and I can reorder this so the 5 goes first and add it with the negative 3, which is, of course, 5 minus 3, which is 2. So that means this is also 2 as well. So there are kind of little things that you can do, tips and tricks right there. Remember, when your positive number is bigger in a subtraction, your result is always going to be positive. When your negative number is bigger, your result's going to be negative. When they're both negative, the result's negative. When they're both positive, the result's positive. And going back to the first sets, if one's bigger, one's smaller in the subtraction there, treat it like a subtraction that you know how to do. So do big minus small. Just make sure you know if your answer is going to be positive or negative in that way. Anyway, I hope that's helpful there. You can always use a calculator to help yourself out. And I have some other things I can help you with forms. If you personally want me to work with you on that, we can. But that's enough of that. Okay, the next question asks, what does HK mean if X, Y are the axes on the graph? Axes, well, there are X and Y axes, but the x-axis is in reference to all of the x values that there exist, and the y-axis refers to all the y values that exist, and those are on, y equals 0, x equals 0. I don't know if you meant to say axes. I mean, HK in vertex form for a quadratic equation is the vertex of your parabola. If you're asking why they use the letters HK, letters are used interchangeably. They're kind of arbitrary. It doesn't really matter what the letters are as long as they're not x and y, because we're using x and y there. I mean, A, B, C, D are often used as constants. I and J are index values for like vectors and imaginary terms and such. F and G are used for functions a lot. I mean, I don't know why they specifically chose to use H and K. H for horizontal, K for vertical. I don't know. No, I don't know. But X and Y for us, and you wrote them as a coordinate pair. They're not axes. I mean, they are axes, but they are every point that's on your graph. When it says y equals and all that stuff, we're saying there's a certain y I get from a certain x, and there's an infinite number of solutions on that parabola. Here's an xy value, here's an xy value, here's an xy value. all throughout the parabola there's an xy value. There's only one specific value that's a really critical point for us called the vertex that's used in vertex form. There's a reason vertex form works the way that it does. I answered it in the last video. That can really kind of help you take that whole thing home. And I hope that answered it. I'm not really sure if it did, but I sure hope it did. All right, the next question is how to tell if a function is being reflected over an axis or not. Well, if we're referring to, the only reflection we'll ever have to talk about is reflecting over the x-axis. Are we flipping it over? And it flips over if your a value, your stretch factor, is negative. So it's something I pointed to earlier on a question about describing the transformations. If you want to see that question, I talk about it. If your a value is negative, you reflect over the x-axis. That's the only one we refer to. Now, why does it reflect over the x-axis? Because we're talking about your y values changing, right? You plug in a value for x, that happens first. Your y value is going to be a result of whatever happens next. What happens in vertex form? Let's see. What happens in vertex form? Well, in vertex form, let's get this out of the way. In vertex form, we take that x, subtract an h from it, and we get some number. It doesn't matter if it's positive, negative, or 0. When you square that number, it won't be negative. No matter what's inside here, it could be negative 1 billion. When I square it, it's still a positive number, or 0. But it's never negative. After you square it, it's never negative. So what happens with this a outside of it if the a was negative every single time with something that you square it? Let's just assume there's not 0 inside of here. When you square it, it's positive. What happens when you multiply by a negative number? It becomes negative. So no matter what you plug into here, becoming positive means this will make it ultimately negative. And that's why negative a does that, because it starts to lower your things. And that's why parabolas hit more than one point, because when you square it, it can... Negative 2 quantity squared is 4, positive 2 quantity squared is 4, and you can see why they get equal heights. But anyway, yeah, when that a value is negative, that's what happens. That end result kind of becomes more negative as a result. Whereas it's always positive, and this is always positive, and it stays positive. So that's just kind of the thing. But you always know if you flip it over if your a value is negative, and that's just the end result of that. All right, with that one down, let's take a look at the next question here. How does the value of k and g of x equals x squared plus k affect the translation of f of x equals x squared? Very specific question. I kind of like it. So right here we have original parent function here one more time, f of x equals x squared. And then we have g of x equals x squared plus k. Now, I don't know if you're asking this as in you truly don't know the answer. Generally, we also even like to refer to an a value, but I'll leave it. Actually, a does not affect your translation, so I might put it in here. And you see these every so often because I want you to recognize if you're not aware of what form this is in, you can consider this either vertex form or standard form, up to you. And it doesn't matter what letters here. All that matters is it is a constant. It is a number that doesn't have an x with it. It's a number that's not in parentheses. So if you want to write it in vertex form, it literally is the letter k out of vertex form. There's a 1 on the outside. This is x minus 0 that's being squared and plus k. That means your vertex is at 0k, which also means that you are going to translate this upward k units. If you're writing this in standard form here, in standard form, the middle term, the bx, the 0, here, oh, there was that mosquito thing. The b value is 0, that's multiplying with that x here, and your c value apparently is k as you put. Your y-intercept of this guy is at 0, k. And you know what this does show you here is if your b value is 0, then there's no horizontal translation, just like if your h value is 0. These are different numbers. I mean, these are both zeros, but h isn't always b. If h was 1, b wouldn't suddenly be 1, is kind of what I'm saying there. The point is the vertex and the y-intercept are the same thing. So how does it affect your translation? It goes either vertically up or vertically down, and your vertex is on the y-axis. The y-axis is your axis of symmetry. There is no horizontal translation. So it goes up or down k units based on what's there, and that's it. I don't talk too much about that because I do want you to recognize the original form and not try and think about, when do I plug in this one to solve for a? When do I do this? Because I know IXL did that a lot, and it kind of screwed people up more than it should have. All right, next question is when you graph y equals a times x minus h quantity squared plus k, why is the line curvy instead of straight lines? Why does the exponent do that? Ooh, I could answer that in too many ways that I'm, again, time-wise, I shouldn't be able to here. Let's think more, let's think less about the curvy versus straight. Let's think more about the idea of, well, Okay. Let's think more in terms of dimensionality. And I'm going to just be with you for a moment here. By dimensionality, I mean one dimension versus two dimensions and things like that. Okay. Let's say that I have, let's see, what's something we'd want to compare something with. Okay, let's say we have two different TVs, right? Let's say I have, and by the way, televisions are measured diagonally in length from one corner to another corner. Let's say I have a 30-inch TV and you have a 60-inch TV. Okay. As far as length goes, your television is twice as long as mine. Here, I will draw this. So let's say I have, once again, a 30-inch TV. Boom. Measured across is 30 inches. And then you have a 60-inch TV. I'll kind of take this and I'll try and double it here. Let's say that's about doubled. Yours is a 60-inch TV, right? Now, they maintain the same ratio, which is kind of important what we're talking about. They're both widescreen, whatever. Hey, your TV is twice as long, okay? But the thing that we might not be, but you just compare dimensionality of length, which just goes this way and this way, this way and this way. You see, if this length was X and this length is Y, you have to keep in mind that everything grows similarly in every way as long as these objects are similar in ratio. What I mean is this would be twice the amount of X and this would be twice the amount of Y. So yeah, everything's twice as long. That's great. The thing that you're missing out, of course, is talking about area. How much bigger is your TV than mine in terms of area? Look, if I place this over here, and I know I didn't do this perfectly, but you should be able to fit one TV, 2, 3, and 4 in there. How come? Because the area takes both 2's into account when you multiply that by them to get 4, right? The area of the small TV is XY, and the area of the big TV is 2x times 2y, which is 4xy. It's 4 times bigger. What you might be neglecting to understand when it comes to squaring something is that something is multiplying by itself. It's not multiplying by a constant amount. If something multiplies by itself, it's growing in both directions of dimensions. I don't know if I'm answering this very well, but it grows in both dimensions of directions. 1 times 1 is 1. 2 times 2, which is twice as much as 1, is 4. 4 is 4 times more than 1. 3 times 3, which is 3 times as much as 1, is 9. 9 is 9 times as much as 1. So notice how you don't see, I'm not just 3 times larger. I'm 3 times 3 times larger. When you square something, you're looking in 2 dimensions. That's why I'm bringing up the TV thing. You're looking in 2 dimensions, not just twice as long in one direction, right? It's not like this TV goes like this, where it's only twice as wide but the same height. It's twice as wide in both directions, and kind of that's what happens when you square it. Now, why is it a curve instead of, say, angled? Because you might understand, okay, that's why I plot those points, because you understand that, right? You plot points in a table. So if I have 0, 0, 1, 1, 2, 4, 3, 9, you might be asking, why do I not just draw a straight line here and a straight line here and a straight line here and angle it? Because every point in between is considered, right? What about 0.5 squared? What about 1.5 squared and 2.5 squared and the numbers be in 1.75 and things like that? Everything gets squared and there's a progressive increase. There's never one constant rate of change. It always increases because squaring a larger number gives you a greater scale difference than squaring a smaller number. Like, again, 1 square, even though 3 is 3 times more than 1, 3 squared is 9 times the amount of 1 squared. Right? Squaring a larger number gives you a greater discrepancy because you're doing 3 times twice. You're doing times 3 here, times 3 there. Anyway, I could get really deep in that. I kind of sort of did, so I'm gonna. But anyway, but that's kind of why it is. I hope that helps you. All right, got 3 more questions here. Can you have a quadratic graph be tilted? Oh, can you have a quadratic graph be tilted? If so, that means the line of symmetry would be tilted at an angle as well, right? I personally have not dabbled in that kind of abstract form really before. I know you can. I don't know what kind of equation does it. I'll let you know this to start off. It's not a function. So while quadratic equations are functions, there are these things, and this probably isn't what you're asking, but there are sideways parabolas. These ones, I know the equations of these ones. You kind of swap x and y. You can get yourself equations. You know how we do some y equals x squared mumbo jumbo? Try x equals y squared. You'll get something like this. Okay, now these are also not functions in and of itself. These fail the vertical line test. But you might be asking about, by the way, this is the axis of symmetry. So it's tilted with it. So to answer your question, yes. Yes to everything. But you might be talking about a graph that looks like this. And a graph that looks like that is not to be trifled with. No, a graph that looks like this, I couldn't tell you what the equation things are, but what I could tell you once again is it fails the vertical line test, so it's not a function. Most of the ones that are like this probably fall in the form of not conic sections, but something where you probably have an x squared somewhere and a y squared somewhere. Now, if you're not too careful, you'll just end up making a circle. So I'm sure there's something that has to do with this. Other manipulations of x and y, like 2x minus 3xy. And so there's probably some really weird stuff that goes on with this that can help you get that. I do not know what it is off the top of my head. Are there equations like that? Yeah, I think they do exist. I don't know how to bring it about. But the axis of symmetry, to answer your question, remember, the axis of symmetry is not an actual part of the graph. The axis of symmetry is a way of describing that your graph is symmetrical and what line it's symmetrical across. So as long as your parabola is symmetrical, there's always an axis of symmetry that's in that middle. And I'm not sure if that makes sense because it's kind of a chicken-egg question here. What, like as far as which came first. Because there is no axis of symmetry if it's not symmetrical. And if it's symmetrical, like, you know what I mean? So that, yeah, the axis of symmetry just goes along with it. It goes wherever it is, assuming it's symmetrical, assuming it's parabola. But it can be tilted. I don't know the equations for those ones. All right, what equation do we use to find more points on the graph? I don't know what that means. What equations do we use? What equation do we use to find more points on the graph? You use an equation to find points on the graph. That's why I'm confused. I'm sorry, I can't answer that question. All I can say is you use an equation to find more points on the graph, right? We use an equation, plug in points for x, get out values for y, or use your 1, 1, 2, 4, 3, 9, whatever, things like that. I'm sorry, I do not know how to answer that question. Thank you for asking. I'll still give you credit. Can you go over how to graph a parabola again? Oh, okay. Listen, I'll tell you what. I did answer it earlier on a previous problem. I'll show you which problem it was. I answered a little bit about it. It was this one. How does 1, 1, 2, 4, 3, 9 method relate to the table? So I answered it a little bit there. I did answer it in the last video. And I'll tell you what, Mr. Bullock's videos does cover what I do. I don't know if he says 1, 1, 2, 4, 3, 9 and stuff, but he talks about the idea of transforming the parent function by taking what you would originally do and multiplying by your stretch factor. So he does nothing different than I do, but he might say it in a way that can apply better to you. So if you want to look a little bit more on how somebody does it, take a look at what Mr. Bullock does in his videos, because I think they do cover it in a good extensive way as well and kind of fast. So I'm not going to go over it in this video. I'm sorry. It's just, well, I did earlier. That's kind of why I'm not going to here, but I did cover it in the last video. I want to know what it is that you're missing. See, here's the thing. If I go over it again, it will just be me going over it again. What I mean by that is you'll hear the same thing I've always mentioned, so there's nothing new I can really add to it right now, except for something else that you might be doing specifically that's different. So if you want to see me about it, you can, but I also recommend checking out some of Mr. Bullock's videos that I had posted online for you. And for those who are from the outside looking and don't know who this Mr. Bullock guy is, he was another teacher for these kiddos who I still post videos for. He has his own math channel. I think it's called Mr. Math Blog if you want to check it out. And if you want to look at some things on here for how to graph, look at sections 6.1 and 6.2. And he has videos on that explain it pretty much the same way that I do. It's a tableless approach here. And remember, if you don't know how to graph tablelessly, you can always use a table. All right, that's as much as I can say there. All right, so that ought to conclude it for this one, guys. This is Mr. Robinson here. I do hope this was useful for you guys. And if you have any more questions, please let me know. I'll see you guys in a couple weeks for the next Q&A Power Hour video. See ya.